we're going to talk about matrices of specific kinds um, and some operations. I hesitate to call them operations, but let's call them operations on matrices. So the first one is the transpose of a matrix A. So the transpose of a matrix A is simply the matrix where every row becomes a column and every column becomes a row in the same order. So it's easier to show you with examples. So if we have 1, 2, 3, 4, 5, -1, if we put the transpose, this is the symbol we're going to use for transpose, a t as an exponent. That means the transpose of this matrix will be a new matrix where every row becomes a column. So 1, 2, 3 row becomes the column 1, 2, 3, and the 4, 5, -1 becomes the column 4, 5, -1 there. So transposing means changing rows into columns and changing columns into rows. Now, if we transpose twice, of course, so if we did the transpose of this guy, this column would become a row, this other column becomes the second row, and so transposing twice gives us back the same matrix. So that is one thing to know. Any matrix, doesn't matter which one you have, if you take the transpose, and then you take the transpose of the transpose, we end up with the original matrix we start with. So transposing twice gives us back the same. There's an analogous property about inverses. Do not confuse inverses with transposing. The inverse twice gives us back the same matrix, assuming that the original matrix is invariable. Some matrices are not invariable, but if they were invariable and we find the inverse of the inverse, we end up with the original matrix, just like when we take the transpose of a transposed matrix. If you happen to have, so this is not necessarily an example, I should scratch that and just call it a fact. It's something that it is, something that is rather. It is just those two things are facts. If you have a lower triangular matrix and you transpose it, so I'm going to use L for lower triangular matrix. So that means there's zeros above the main diagonal. If we transpose that, we're going to end up with an upper triangular matrix. So this is just saying some generic, I'm not saying any specific one, but, and then that's going to give us an upper, when we transpose a lower triangular matrix, we end up with an upper triangular matrix, and vice versa. So these are facts. Let's 1, 2 separate facts. This is another fact. If you take an upper triangular matrix and you transpose it, you end up with a lower triangular matrix. There are many more facts that we can derive. So for instance, if you add 2 matrices and you take the transpose, well, you could take the transpose of each one of them and then add them together. So we got 1, 2, 3, 4, 5 facts. It depends how you count. The reason why I'm saying that is because some people may count that as 1. And this really has nothing to do with transposes. So you could perhaps disregard this when you are counting. So we got 1, 2, 3. It depends how you count. It is good to know all of those facts, though they're handy. The next one is very, very important. A, B, the transpose is not the transpose of A with the transpose of B. It is B transposed A transposed. And one way to think about this is when we multiply on the left, we are changing rows. If we transpose, then, well, let me back up a little bit. Again, if we're multiplying on the left of the B, we are changing its rows. If we multiply on the right, we're changing the columns. But then the transpose of that is not rows anymore, it's columns. So everything fits well. It works well. Yeah. So in a way, moving this to the other side changes something else. But then this one has the appropriate change anyhow. That's the way I'm thinking of that. By the way, there is a very similar property with inverses. The inverse of AB is equal to, whoa, no, B inverse A inverse. So the order gets reversed just as with the transpose. Yeah, that is an important property. A very, very unexpected property, in my opinion, is that the inverse, when transposed, gives us the transposed, the inverse of the transposed. In other words, transposing and inverse commute. You can exchange those two. You can put them in any order, and we will end up with the same output. Having said that, be careful, because when we have a multiplication and we want to distribute any of the transpose or the inverse, we have to swap the order. The order is changed. Yeah. Let's think about an example or a couple of simple examples. Let's multiply 1, 2, 3, 4 with a column vector 5, 6. Okay, one way to think of this is as, okay, so we're doing 5 and 1 and 6 and 2, 5 and 3. So 5 is affecting 1, 3. 5 times 1, 3, and 6 times 2 and 4. Yeah, so we end up with 5, 1 plus 2 and 6. So that is 5 plus 12, 17, which is what's going on here. 5 plus 12 is 17, and then 15 plus 24, just as we would get the same numbers here. Where did I say 15? 5, 1, 3, 5, and 12. 15, oh yeah, there's a 15, and 24, 24. And then there's the 12. So this works correctly. If we multiply the row vector 5, 6 times the same matrix 1, 2, 3, 4, we end up with 5, let's say 5, 1, and 5, 2. 5, yeah. So 5 times the row 1, 2 plus 6 times the row 3, 4. 6 times the row 3, 4. Yeah. So multiplying on the right, well, actually, multiplying this with this vector provides a linear combination of those columns. Multiplying on the left gives us a linear combination of the rows. Yeah. So again, this is a linear combination of the columns. This is a linear combination of the rows. If we switch this to the other side and we do the transposition, yeah, if we were to do 5, 6, and we did change these rows into columns 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, then we end up with 5. The row would be 1, 3, 1, 3, plus 6 times the row 2, 4, which is very much the same as that. So if we transpose, if we were to change the order of those two, if we work with the corresponding transposes, then we would be okay. Yeah, then we have an equivalent product. All right. From this, we can also derive this equation as well. I'm sorry, not that equation. This equation. Yeah, this equation. Let's see how we derive this fact from this fact. Well, or from this one rather. Anyway, let's derive this, where this comes from. So A, so this is a new idea. A inverse equals the identity. Let's transpose on both sides of the equation. So A inverse transpose equals the identity transpose. Now think about the identity. The identity is a matrix that has ones in the main diagonal and zeros everywhere else. So when we transpose this row, or rather this column becomes the row, which is exactly the same. The second column becomes the second row. It is the same either way. Whether you're talking about columns or rows, they're the same ones. What I really mean to say is if we exchange rows with columns, we're going to end up with the same matrix. By the way, those kind of matrices where if you transpose, you end up still with the same matrix are called symmetric matrices. Symmetric with respect to the main diagonal. So transposing I, the identity, is going to give us the identity. Transposing a product means A inverse transposed A transposed. So that means that if a matrix multiplied with another matrix gives us the identity, that means that this matrix happens to be the inverse of this matrix. Again, every time you multiply two matrices and we end up with the identity, that means that one is the inverse of the other. So the conclusion of that is that this is T. So the transpose of A inverse is equal to that matrix precisely. A inverse transposed. And this shows, this is a little proof that we can exchange, we can commute the transposition with the inverse operations. Again, I hesitate to call them operations, maybe operators is a better thing to say. And it relies on the definition of inverse, which it relies on the definition of identity. And then it relies also on the fact that when we have a product and we transpose, we have to reverse the order in order to distribute the transposition. And then back again to the definition of identity, or definition of inverse matrix rather. Okay, let's talk about the dot product. And transposes. Let me just check something. Transpose of a matrix, the dot product, and this. This is interesting. Let's look at an example. Let me make sure my example numbers are good. Yep, example number 3. Consider the vector 1, 3, 5 multiplied with the dot product with 2, 4, negative 1. Okay, we know how to handle this. It is 2 plus 12. minus 5. So that is 9, the number 9. We can think of this dot product as the matrix multiplication 1, 3, 5 with 2, 4, negative 1. So notice that this matrix, there is no need to put a dot. We don't have the dot product because this is a matrix that is 1 by 3. This matrix is 3 by 1. And we know how to multiply matrices. You know, it is um, almost the same as the dot product, except that one is horizontal. And we're multiplying this row with this column. So we have 2 plus 12 minus 5. Um, Technically speaking, there is a difference though, because the product of multiplications, not the dot product of vectors, this is the dot product of vectors. The product of multiplication, rather, the multiplication of vectors, back up, the multiplication of matrices should be a matrix. So technically speaking, these are the computations, we should end up with a 1 by 1 matrix. Here, we don't end up with a 1 by 1 matrix. We end up with a number, a scalar. So technically speaking, those two are not the same. However, we're going to make a connection between the two, and we're going to label them as the same. Technically speaking, they are not, because the product of matrices yields a matrix. So here we have a matrix, a 1 by 1 matrix, and this is just the way we compute the 9, but this is still a 1 by 1 matrix, and this is a 1 by 1 matrix. And this is not a matrix, this is a scalar, a number, and this is the way we compute the number. So technically speaking, they're not the same. However, we're going to make a connection between the two. It's a little informal, but acceptable. Likewise, well, I shouldn't say likewise. In contrast, let's see, 1 by 3, we can multiply 1, 3, 5 with 2, 4, negative 1. And that's not going to give us a 1 by 1 matrix. That is going to give us a 3 by 3 matrix. Let's see. Why? Because we're multiplying rows with columns. The rows and columns are very short. So 1 times 2, 2. 1 times 4 is 4. 1 times negative 1, negative 1. But then we move down to the next row. 3 times 2 is 6. 3 times 4 is 12. 3 times negative 1 is negative 3. 5 times 2 is 10. 5 times 4 is 20. 5 times negative 1 is negative 5. So now we have a 3 by 3 matrix, which makes sense because this is a 3 by 1, 1 by 3, and then 3 by 3. So here we have the three cases. Dot product of two vectors that are of the same size, so we cannot really multiply them as matrices because the sizes don't match. Then we have a proper matrix multiplication and another proper matrix multiplication. This is also called the inner product. Sometimes we abuse the language and we call them the dot product, but this is more formally called the inner product of those two vectors. Well, those two vectors, the inner product. And the outer product of those two vectors is this. So pretend this is the vector x and this is the vector y. So x transposed with y gives us the inner product of x and y. X, y transposed, this one, gives us the outer product of x and y. So we have two products. This video is full with many miscellaneous facts and definitions. Um, One thing that transposes do is that if we have AX transpose, and then let's see, this is, pretend this is a 3 by 3, and this is a 3 by 1. So that makes sense. And we end up with a 3 by 1 vector. When we transpose, we end up with a 1 by 3, allowing us to multiply by a 3 by 1 vector. So pretend those two X and Y are vectors and column vectors. And A is a matrix. So the transpose allows us to sort of commute X and A. We cannot commute, of course, but we can sort of commute it and have this as X transpose times, this is a transpose here, not an inverse. Gotta make sure we don't confuse them. Y. Yeah, so the Y does not change, it is the same. And what we are doing is um, thinking of a multiplication on the right with the X in the middle as a multiplication on the left with the X on the left. It allows us to do some kind of commutative properties, not really a commutative property, but it allows us to do that. Again, this section or this video is full of miscellaneous facts and definitions. Symmetric matrices. So a symmetric matrix is the one that equals its own transpose. So when you change the rows into columns, you still end up with the same matrix. So let's say you have the matrix as an example. And again, I want to keep track of the example number. So we did number 3 last. So as an example 4, you know, if you have a matrix 1, 2, 3, now this has to match its own column. This first row has to match its own column because that is the very definition of a symmetric matrix. And consequently, because this has to match its own column, once we display 1, 2, 3, we have to put 1, 2, 3 down in the first column. Now, whatever we put down here, I don't know, 7, 8. This row has to match the second row. So 2, 7, 8, because we already had 2, 7, 8. And then whatever number we have here, it is okay because this column is going to match this row regardless of whatever number we put here. So if we put here a 0, for instance, we're good. So this matrix is symmetric. Notice that if you go down the main diagonal, it doesn't matter what those numbers are. The numbers opposite to the main diagonal, so the 2 equals the 2, and then the 3 equals the 3, and the 8 equals 3. So those numbers have to be symmetric. So sort of like this. If you put this vertically, then we can see the 2 2s, the 2 3s, the 2 8s as mirror images. Well, sort of. If we were truly having an image that was a mirror image, the 2 would be kind of sideways. But of course, I'm not going to do that. We have the same numbers on opposite entries of this diagonal. So that's what symmetric means, and it means the same as that. I'm just trying to see what the next fact is, the one we want to establish. Um, the inverse of a symmetric matrix is symmetric. The inverse of a symmetric matrix is symmetric. The inverse of a symmetric matrix is symmetric. So let's pretend S is symmetric. Its inverse should be symmetric, which means that it should fulfill this requirement. Well, let's take the transpose of it. So we have a symmetric, assume S, and that's why I'm using the letter S for symmetric. It's a matrix that is symmetric. Consider its inverse. We don't know if the inverse is symmetric or not. Um, yeah, let's do the transpose of that. Well, that is equal, as we established earlier, but one of the facts we established earlier was that the inverse and the transpose commute. That means that you can exchange those anytime we want to. So let's do that here. We will have ST inverse, but we're assuming S is symmetric. Consequently, S upper T is equal to S. So we can substitute and have just S to the -1. So there, this matrix S to the -1 is equal by transitivity to the transpose of itself. This matrix is equal to the transpose of itself. Consequently, that matrix is symmetric. Yeah. Yeah. So this proves the statement. What statement? That the inverse of symmetric matrices are also symmetric. All right. We're going to apply some of this to our factorization of matrices that we have done in previous videos. So if we have a symmetric matrix, okay, and we can factor it into three matrices, one that is lower diagonal with ones in the main diagonal. I'm sorry, lower triangular with ones in the main diagonal. D, a diagonal matrix, and an upper triangular matrix with ones on the main diagonal. Okay. If we take the transpose across the equation, so S transpose would be equal to L du transpose. And we can do that. Can we distribute the transpose across this? And the answer is of course, except that we have to put those in reversed order. So U transposed, yep, and then D transposed, and then L transposed. Now, if we assume S is symmetric, then it is exactly equal to its transpose. So this is the same thing as S. This kind of factorization is unique. When we factor out into unit lower unit triangular, unit upper triangular, or upper unit triangular, those two matrices are going to be unique. Well, those three matrices are going to be unique. What this shows is that when we have a symmetric matrix, this guy is equal to, well, actually, this guy is equal to to L. In other words, those two are related. Why? Because the decomposition, the factoring is unique. And that means that this guy has to be exactly equal to that one, those two. So if L and U are the decompositions, the compositions of S, then once you find L, you found the other one. because U is going to be the transpose of L, and that is reciprocal. Um, L is equal to the transpose of the other one. This is interesting. So that can save us some time. Let's perhaps do an example, a short example so the next example is 5. Okay, let's say we want to decompose like more factor. A equals, let's start with something small. 3, let's put 2 3s diagonally, 2 and a 4. Okay. And we want to, oh, wait a minute. Wait. This is not symmetric. Whoops, bad example. Let's cross it off. Because the example I want to show has to be symmetric. And that is not symmetric. You know, yeah. So let's do it the other way. Let's put the 3s on the sides, 2 and 4. All right, so this, in fact, I'm going to change the name to S. So let's start the example again here. Example 5. Sorry to do this. S equals, so it's a symmetric matrix, 2, 3, 3, 4. That is symmetric for sure. And we want to find the factoring into lower triangular and upper triangular. Okay. So, we want to, the way we did it in the previous video was by getting rid of this 3 to get the lower triangular. And the way we did that in this case, let's see. So we want to find 2, 3, 3, 4, a matrix that takes care of that 3, annihilates that 3. So we need to get rid of the 3, subtract 3, but this is a 2, so we have to take care of the 2 also as we do that. So let's see what we get. 2, 3, the 2 simplify, so we end up with negative 3 plus 3, bingo, 0. And then when we multiply those two, we end up with negative 9 over 2. I'm going to do that computation down here. Negative 9 over 2 plus 4. So multiplying the two threes give us 9, negative over 2 plus 4. Well, that is negative 9 over 2 plus 8 over 2, and that is negative half. So that's the number that goes here, negative 1/2. And that is an upper triangular matrix. So again, we want to factor this out. It is not factor. What we are doing is multiplying with this matrix to get to an upper triangular matrix. So what we need to do, so remember from the previous video, this is our elimination matrix. And so because it did eliminate the 3, it caused this to show up, but that's all right. And we really want the inverse of that. And I just want to double check. What is the inverse of 1, 0, negative 1/2, 1? I claim that it is 1, 0, positive 1/2, 1, but let's double check. So the only reason why I'm doing this is to double check that this is the inverse of that. Because if I want to factor the S, this is S, I want to move this to the other side of the equation. But so we have to multiply by the inverse to get to the other side of the equation. But inverses in matrices are very, very tricky. So just double checking. So that is 1, 0, and then negative 1/2 plus 1/2 is 0, and then 0 and 1 is 1. So sure enough, this is the identity. Rather, this is the inverse of this. So we multiply by this matrix on both sides of the equation on the left. So S, which is 2, 3, 3, 4, is equal to this matrix, 1, 0, half 1 times the upper triangular matrix. So this is the form U, rather LU, um, 2, 3, 0, negative 1/2. Boy, this matrix is simple enough, but that's okay. However, we want to factor this further into an upper unit triangular matrix. So this is not unit triangular. It is upper triangular, but not unit triangular. We want to have ones here. That's easy to fix. We can factor out the 2 and the negative 1/2. This is a diagonal matrix, which is symmetric, by the way. Notice the zeros. And we end up with 1, 3. I lied. It's 1. We factor out the 2. So we should have 3 halves. And I'm in a pickle because the point I wanted to make is that this should be the transpose of that. Those two should be transpose of each other. And they are not, because this one has a half on this corner. This one has 3 halves on that corner. Let me find the mistake. Of course, the mistake is a typo. Yeah, it is a mistake nonetheless. So I'm not minimizing it. It is a typo. We have negative 3 halves. And I copy down negative 1/2. That should be 3 halves. And that should be 3 halves. And just to double check, that still gives us the same identity. So that means that this is the lower matrix, lower triangular matrix. So that should be 3. And that consequently, this should be 3 there. So it's good that I did this, because that's one way to know that we made a mistake. This matrix, our lower unit triangular matrix, should be exactly the transpose of this matrix. Exactly the transpose. So they're the same. So if you look at this row, it is very much the same as this column. And this second column is exactly equal to this row. Well, except that they are in different positions. This is D, the diagonal matrix, and this is the upper unit triangular matrix, and they are transposes of each other. That will happen every time we have a symmetric matrix, which we want to break up into parts. Yeah. I'm trying to think if there is a shortcut, because once you have this matrix, then we know what this matrix should be. But then the question is, how do we get these numbers? Those numbers came from the matrix before 2 and negative, before it became unit triangular. Okay, something to think about if there's a shortcut. Okay, let's talk about permutations. A permutation is a rearrangement of anything for that matter, but in particular of a list of things. So let's say we have 4 objects, A, B, C, D. And we can put them in a vector. So this is a row vector. If we have another, I should have started with a column vector. Well, so it's not a problem. I'm just going to rewrite A, B, C. Actually, let's make them shorter, A, B, C. Any rearrangement of the letters, it is going to be permutation. And in fact, no rearrangement of the letters is also a permutation. So this is one permutation of the letters A, B, C, comma. A second permutation will be A, C, B. So again, any rearrangement, and we exchanged C and B, um, comma, or if you put the B on the top and then A and C after, that's another rearrangement, or B and then C and A is another rearrangement. And there are two more that I'm missing, C, A, B, and C, B, A. All of those are rearrangements. Um, and all of those are permutations, so scratch that. Permutations of any of them, actually. You can start here and then permute them, and you end up with the other five. You can end up with any of them because um, who is to say that the alphabet was ABC and not BCA and then D, F, G, you know, why is A the first letter? Well, there is probably a good reason why, but what I'm trying to say is it doesn't matter which one you start with. You know, they could be objects, triangle, star, square. There, which one is first? We don't know. Um, but then you can rearrange them and end up with the other five. And there is a total of three um, elements that can be permuted. And each one of those is called a permutation. We can think of permutations also as functions. So, yeah. So F1, for instance, of ABC can be ABC. So this can be thought of as a permutation, which leaves everything alone. F2 of ABC is, if we think of ACB, so this permutation changes the last two. Now, don't think of B and C, don't think of the letters. Think of the positions, the relative positions they have. Because if we apply F2 to 7, 9, 10, okay, F2 is labeled, we're labeling as F2 the permutation that exchanges the last two. So that is 7, 10, 9. So don't focus on the ABC, focus on the relative positions. I just want to give you a quick analogy because this happens all the time in other classes. You know how you got the Pythagorean identity, A, B, C, and everybody knows A squared plus B squared, whoops, equals C squared. Well, what I do in many of the classes I teach is I change the letters around on purpose, C, A, and B, and I keep the same letters, but just in different order. Uh, well, it would be naive to think that, and my students know that well, so they know not to make that mistake, to think that, oh, so C squared equals A squared plus B squared because that's how the formula comes. Well, no, 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 no. What we have to understand or remember is that it is the hypotenuse, the one that equals the sum of the other two after we square each one of them. So in this picture, A squared equals B squared plus C squared. And of course, you know that. I'm just trying to make an analogy here. So when we say that F1 of ABC equals ABC, or this one, BC changes into ACB, we are not saying that the letters are the ones that change, but the position, whoever is in that position. So, oh, even better, F2. So once we establish that, what is F2 of CAB? There we go. So from here to here, what is the answer? Well, let's think. It will be, we want to exchange the last two. I don't want to exchange B and C. B and C are the first and the last one. But what this permutation does, and remember, we're thinking of a permutation as a function. What a permutation does is that it changes the numbers in whatever position they are. So it changes those two. So changing those two give us C, B, A. Yeah, yeah. And then we can mount one on top of the other, one a permutation on top of the other. So let's say F3 is of A, B, whoops, I didn't mean that. F3 of A, B, C equals, so I'm declaring what we're labeling as F3. Let's say it is this one, BAC. So what does it do? It bumps the B up. Oh, it exchanges the top two. F2 exchanges the bottom two, whatever they are. Okay. Okay. So F2, remember, exchanges the bottom two. F3 exchanges the top two. So what happens if we have, I'm just going to use something else, numbers. So 1, 2, 3. We don't have to have A, B, C. Okay, so exchange the bottom. I'm going to do this in 2 stages because sometimes I cannot think that advancedly. So exchange the 2 bottom ones, 1, 3, 2. But then when we apply F3 on it, we exchange the first 2. So that's going to give us 3, 1, 2. Okay, let's do the same in reverse order. By the way, the operator is applied on the left of the thing to be operated. So we go in this order. Yep. So F2, F3 of 1, 2, 3, because I want to compare what it does. So F3, remember, swaps the first 2. So we have 2, 1, 3. F2 swaps the bottom 2. So we end up with 3, rather 2, 3, 1. Okay, let me just double check. So exchange the bottom 2, then exchange the top 2, and we end up with 3, 1, 2. Exchange the top 2, and then exchange the bottom 2, and we end up with 2, 3, 1. So we do not end up with the same thing. So applying permutations in different order provides us with different answers. Sometimes it doesn't. Sometimes we end up with the same answer. For instance, if you apply, this is a sort of a silly example, F2 on F2, you end up with the identity. The same thing as, it doesn't matter which order you put it. But anyway, by the way, the permutation that does not change anything at all is called the identity. I just inadvertently said that, and it's true. I mentioned that if a permutation leaves 1 to 3 alone, so F1, the one we called one, the one that takes A, B, C, and gives us back A, B, C, is the identity permutation. Is this looking a little bit familiar? Well, it is, because it matches perfectly. It is looking familiar because it matches perfectly with certain matrices. So we have permutation matrices now. Permutation matrices. So there's a permutation matrix. There's a matrix which will take A, B, C, and let's see, and just for as an example, and it will take it into a C, B. So it exchanges the last 2 elements in this vector, column vector. What we do is take the identity matrix and exchange the corresponding elements that we want to permute. So you know the identity matrix is, for a 3 by 3 identity matrix, will be 1, 0, 0, 0, 1, 0, 0, 0, 1. if you want to have the effect of permuting the last two rows, the last two elements, all you have to do is exchange those two. 1, 0, 0, oh, 0, 0, 1. I was going to put 0, 1, 0, but I want to exchange them, and then 0, 1, 0. There we go. Let's double check. So that picks up the first element, puts it here. That picks up the last element, but puts it on the second row. And then we pick up the middle element, B, but it puts us on the last row because we are multiplying this last row with a vector. All right. So if you want a permutation, all you have to do, and that is a permutation, that is the identity permutation. But if you want a permutation that is different, all you have to do is rearrange accordingly the rows of the identity matrix, and that will do it. So this guy is called an identity, no, a permutation matrix. All it does is exchange the rows of a matrix in the same way as this matrix is obtained by permuting rows of that other matrix. Okay, let's go back to elimination, well, actually factoring of matrices. Back to factoring. Okay, so let's do an actual example. I'm trying to think what example number we should do next. 6. Example 6. Although we could think of all the permutations we did as an example in itself, but that was more of showing you the permutation. So we looked at all the permutations of 3 elements. A good question to ask is, well, there are 6 permutations of 3 elements. How many permutations are there for 4 elements? And how many permutations are there for 5 elements, and so forth? Permutations for 2 elements is easy, just 1 and the opposite. So there's only 2 permutations for 2 elements. 6 for 3, for 4. Figure it out, please. Let's say we want to factor. And by factor in this, at this point, we mean lower unit triangular and upper unit triangular. Factor the matrix 1 to 3, 1 to 4, 5, 6, 7. Okay, so let's pretend we want to do that. That's just that something was not supposed to be there. There. Anyway, and let's use the elimination method that we've been using since the previous video. So we want to get rid of this guy and this guy. Let's do that in one shot. So we're going to multiply by a matrix 1, 0, 0, 1, 0, 1, and 0 here, so that when we multiply with 1, 2, 3, 1, 2, 4, 5, 6, 7, we end up with 1, 2, 3, and 0, 0. We want to wipe off the first column. So, well, except for this unit, for this one that is sitting there. So to wipe this off, we take this guy and do -1, because then we can subtract the first row from the second row, and we can take away 5. There we go. And that will do it. Let's just make sure. So this picks up the first element on each column, -1 plus 1, and nothing. So that's 0. -2 plus 2, 0. -3 plus 4, 1. And then we have -5 plus 5, -10 plus 6, negative 15 plus 7. Okay. Now we want to get rid of this 4. In order to get rid of this 4, we need a number here that multiplied. Um, but here, maybe we can use that number. But the problem when using this number too, because that will work really nicely, multiply by 2 and then add it onto here. When we do that, this 1 is going to multiply by 2 and it's going to move in this position. So a 2 will show up. Can we get rid of the negative 4 using that? And the answer is absolutely yes. But that will create a problem because then we got to fix this one. That's going to create a 2 here. And then when we fix this one with the same first row, that's going to create a negative 4 again. So we're going to have a cyclic problem. Fix this one, but that's going to create this problem. And then fix this one, and that creates this problem. And you know, it goes back and forth. So you can never get rid of the two of them. So this won't do. Can we factor the matrix? And the answer is yes, but we need another matrix. It would be ideal if this guy was up here instead. If we were to exchange those two rows, then the matrix would already be a upper triangular. So this would be our U that we need. Yeah, so that is a place where we need the permutation matrix. So let me label the first matrix as A. Okay. There are two modalities to do when doing this. At this point of the game, we can label this as E1, so elimination matrix 1, because it eliminated those. And then we can permute. Let's do it that way. Okay. So we apply this and we get to this. But now we are stuck. We can't get rid of this negative 4. Can't get rid of this negative 4 because we need something here, something other than 0 that will wipe it off. You know, if we throw zeros here, that's like throwing air. Nothing is going to happen. See, we threw up ones or negative ones to this, and we threw we threw negative ones again. How many of them? 5 negative ones, and that annihilated this guy. It killed this guy. By annihilating, we mean we turned that into 0. But we can throw zeros to something, and that's not gonna matter. Yeah. It's like trying to I don't know, trying to hit somebody with a feather. They're gonna laugh. You're gonna make them laugh if you do that. So no, we cannot do that. I mean, that's not going to achieve the goal. Yeah, of course we can do it, but that's not going to achieve any goal. So what we do at this point is multiply with a new matrix. So remember how we did this process? We did 1 by 1, and we took this matrix 1, 2, 3, 0, 0, 1, 0, negative 4, negative 8, and we multiply by the next one, which is going to be, let's see. Oh, we want to exchange those two. So the first row is as is, 0, 0, 1, 0, 1, 0, and that will achieve our goal. So we have 1, 2, 3. This picks up the last row, but places it on the row from here, but places it on the second position, second row position. So 0, negative 4, negative 8, and then we take the middle row and position it in the last row. So 0, 0, 1. Okay, that's already upper triangular. So we don't have to go any farther. And we call this permutation, a permutation matrix. So what has happened this far is that we started out with A, the matrix A. We applied E. There's no need to put E1, I suppose, because there's only one E. Then we put the permutation matrix, and that gave us an upper triangular matrix. Okay. Um, So now we need to multiply on both sides by the inverse of P. The inverse of P. We have not spoken about the inverse of P. What is the inverse of P? Well, now we got to take the time to figure that out. I believe if P is a permutation, 1, 0, 0, 0, 0, 1. Oh, this permutation, I understand this permutation, because let's just double check. This permutation changed the last two rows. You flip them, you swap them. So what other permutation will swap the last row, will bring us back to the same? Well, itself. 1, 0, 0, 0, 0, 1, 0, 1, 0 will give us the identity. I usually check my identities. So of course we get, well, or the other way to think about this exchanges the last rows, which is, so this row is placed on the second position, and then this row is placed last, and sure enough, we have an identity. So this matrix is an inverse of its own. That's kind of interesting, just like the identity is an inverse of its own. So I don't think that is the case for every permutation, though. They're not inverses of their own. Not every permutation is an inverse of its own. So that means that we can just multiply both sides by P. So if we, let me do it the way they do it in algebra 1. Okay, so multiply by P, and those two cancel. It's like when you're solving an equation. And then we multiply by the inverse of this. So now we have EA equals PU. And then we multiply by the inverse. Those two cancel, but then we got to multiply by the inverse here. So what is the inverse of E? 1, I'm looking at the columns, 1, -1. And I like to double check my inverses. So we have 1. I claim that the inverse is going to be 1, 1, 0, 5, 0, 1, because that undoes what this elimination matrix did to start with. So, yep. And then 1, -1 plus 1, 0. And then we just pick the second element and the last element. So that's 0 on this row. And then -5 plus 5 is 0, 0, 0, 0, and then the 1. So sure enough, this is the inverse of E. This is E inverse. This is P inverse. So can we rewrite A? Can we factor A as a lower? This is a lower triangular matrix. It is, let's write it down. 1, 1, 5, 0, 1, 0, 0, 0, 1. So this is lower triangular. A permutation matrix, 1, 0, 0, 0, 0, 1, 0, 1, 0. And an upper triangular matrix. Where's the upper triangular matrix? I lost it. It's up here still. This one, 1, 2, 3. 0, -4, -8, 0, 0, 1. So we have a lower triangular matrix, an upper triangular matrix. That is not unit triangular matrix. We have this P, a permutation matrix which we did not used to have in the past. I guess we need our D still because, yeah, we would like to take care of that -4. So, okay, so A equals 1, 0, 0, 1, 1, 0, 5, 0, 1. Then we got our permutation matrix, 1, 0, 0, 0, 0, 1, 0, 1, 0. And then we're going to break that up into a diagonal matrix with 1, -4, 1 in the main diagonal. And that 1 is not quite lined up correctly. And then we have 1, 2, 3, 0, 1, 2, because we are factoring out -4 out of those two, 0, 0, 1. And I double check just to be sure. So we get 1, 2, 3, and then we get 0, -4. Yep. -8. And then, yeah. So we end up with a lower unit. I'm going to say L U, little u, so lower unit triangular matrix. Upper unit triangular matrix, so ones. A permutation matrix and a diagonal matrix. So we are able to factor A into that. This is one way to factor A into pieces, and that's all the pieces you will ever need. You'll need a lower, an upper, possibly a permutation, possibly, and possibly a diagonal. If those numbers are not 1 to start with, then you need a diagonal. And by the way, that's true if A is invariable. If there's an inverse, we may do that. If A is singular, if there's no inverse of A, then we cannot do that. We cannot factor an A into lower and upper triangular. That's not going to happen. Really, those are the two main characters of this factoring, and those two are auxiliary elements for this to work. Although some people don't like this factoring. This particular element gets kind of on the way. It's not symmetric. See, there's a sort of a symmetry. There's zeros. There's, so even though this is not symmetric itself, there is zeros up there. There is zeros down here. So that brings some kind of symmetry on those two. And this is definitely symmetric. This one kind of gets on the way. So oftentimes we do not use this factoring. Sometimes we do, but oftentimes we don't. So let's redo this problem differently. And I'm going to show you how to factor. So one way to factor is this way. The other way to factor, let me start with example 6 again. So A equals 1, 2, 3, 1, 2, 4, 5, 6, 7. Okay, so instead, we can think, oh, there's 2 2s. That's gonna mess up the 1 here. We can sort of anticipate that this little bit, the 1, 2, and the 1, 2 are the same. Actually, they don't even have to be the same. If this was 4 and 8, or 5 and 10, if it was a multiple of this line, those two, if the second two were a multiple of the first one, that's going to mess up our possibility of getting an upper triangular matrix. So what we could do is exchange those two ahead of time and not factor A. So we're going to modify the problem. Modify PA, rather modify A so that we don't have to have a permutation. So 1, 2, 3, permute that and put 5, 6, 7 on the second and 1, 2, 4 last. That's going to create 2 zeros here, but that's okay because on an upper triangular matrix, 2 zeros here on the bottom is a good thing. 2 zeros in the middle at first is a bad thing. And the only reason why it is bad is not that an upper triangular has to have them or cannot have them, but the problem is that then we cannot eliminate. It messes up our elimination process. So instead of doing that, we exchange the rows that are going to cause the problem and then worry about this. This problem is going to go a lot smoother instead. So keep in mind, this P, by the way, is the same matrix 1, 0, 0, 0, 0, 1, 0, 1, 0 that permuted the last two rows. That's a permutation matrix. All right, and then let's work with this problem instead. Okay, let's see, something times 1, 2, 3, 5, 6, 7, 1, 2, 4, and we want to get rid of those two. So 1, negative, 5, negative 1, 0, 0, 1, 0, 0, 1 will do. We end up with 1, 2, 3, negative 5 plus, negative 5 plus 5, 0, negative 10 plus 6, negative 4, negative 15 plus 7, negative 8, negative 1 plus 1, 0, negative 3 plus 4, 1, and the middle one I forgot to do. Oh, negative 2 plus 2, 0. There we go. So this is already an upper triangular matrix. So mind, this is not A. What we did is, okay, so if I was asking for the factor in the PA U, rather LU form, so the P, well, okay, the PA equals LU form is 1, 0, 0, 0, 0, 1, 0, 1, 0. That's the P. The A, that's the original matrix, 1, 2, 3, 1, 2, 4, 5, 6, 7. Equals the lower matrix, which is going to be 1, 0, 0, 5, 1, 0, 1, 0, 1, and our upper triangular matrix, 1, 2, 3, 0, negative 4, negative 8, 0, 0, 1. This is the PA equals LU form. Of course, we could ask for the PA equals LDU form. So that would be another problem. Another form, that would be PA equals LDU. So permutation original matrix equals lower unit triangular matrix on the right, upper unit triangular matrix, and a diagonal matrix. So the only thing you would have to do is pull that negative 4 out with a unit matrix with a negative 4 in the middle of that unit matrix. So yeah, make sure you know how to factor matrices. And there are two ways to factor them. one way would be A equals LPDU. And if P or D are identities, then don't worry about them. Then don't write them out. Just put L and U. Or PA equals LU, or PA equals LDU. I suppose, yeah. I suppose we can have A equals just LU, but in that case, we wouldn't need a permutation. All right, so all of this is about factoring. Oh, one more definition. If a matrix, let's call it O, fulfills, what does it fulfill? That the transpose is equal to its inverse. Yeah. Then we call this matrix orthogonal. An orthogonal matrix. So an example of an orthogonal matrix would be the permutation matrix we dealt with in our last example. So it was 1, 0, 0, 0, 0, 1, 0, 1, 0. Yes. This is an orthogonal matrix because, yes, the inverse is itself. And because this is also symmetric, the transpose is itself. So the inverse and the transpose are the same of this matrix. So this matrix is an example of an orthogonal matrix. The column vectors happen to be orthogonal. Orthogonal means that the dot product is equal to 0. And while there's one more thing. The columns are unit vectors also. Yeah, so this is a unit vector, unit vector, unit vector. So we will explore orthogonality at some other point, but it is important to know that what orthogonal matrices are. Orthogonal matrices are the ones whose inverse matches exactly the transpose of the original matrix. And this is one example of them. All right, with this, we close this video.